Hey everybody, welcome back to our Materials Informatics playlist. Now, in our previous video, we were covering generative models, GANs, VAEs, so you would think that this video would be about diffusion models. And we're going to do that in our next video. And that's because diffusion models rely on something called UNIT, and that came out of the field of image segmentation. So today we're going to do a brief interlude over to talk about image segmentation, but if you're really dying to talk about diffusion models, check out the next video. But be aware, they will talk about something that we haven't yet covered because it's covered in this video. So let's dive into it. Image segmentation has become a really important part of materials informatics, right? In fact, there's whole people that's really just what they do. They don't do property prediction, they don't do classification, they do segmentation. All right, so let's define it. First off, image segmentation is this process of taking an image and partitioning it out pixel by pixel to figure out which pixels should belong together, right? And which ones should not belong together, right? So this helps for lots of different things. If you take a look at this image on the right, you've got a microstructure, and then you've got clearly different aspects to it, right? You've got this sort of dark gray region, this sort of speckly region. So these could correspond to lots of different things in a materials, microstructure. I'd have to know this exact paper to know what they're talking about, but these could be grain boundaries, these could be maybe defects or impurities or secondary phases, lots of different things. They could be regions in between. And so what you see on the three examples below is examples where there have been labels added, either by hand or using image segmentation models, where the idea is that you could train a model such that it could automatically figure out which region, is this light blue, which one should be this dark blue, which one should be this green region, which one should be the orange region. That's going to be really helpful for a lot of different materials processes because microstructures can be converted into features after you've done segmentation, right? Maybe it'd be easier to calculate, what's the overall volume fraction in one phase, or what's the continuity, or what's the aspect ratio. All of those things come out of image segmentation, right? So what's the goal? The goal is, to make an image more meaningful or easier to analyze by isolating these features of interest from the background or differentiating between these different materials phases, okay? So that's what we want to do. How do we do it? Okay. By the way, recognition versus semantic segmentation versus object detection versus instant segmentation. We need to do a little bit of cleaning up of terms because sometimes these get used interchangeably, but they're not, right? First off, in the top left corner, you see this picture of the sheep and they have the bounding box surrounding them that says sheep, right? This is an example of classification. If it had been a picture of a dog, we would hope that it would have correctly said dogs, right, or in this image. And even better, not just in this image, but in this part of the image, and it would draw the bounding box around them. So that would be classification and localization. We can do a bit further than that, though. We can do object detection, where now it draws bounding boxes around each of the individual three sheep, because it's learned that these are actually three instances, right, of the same type of thing, right? But it's still just drawing bounding boxes around them. If you actually wanted to go pixel by pixel through this and say, this here is sheep, this here is road, this here is grass, now you're talking about semantic segmentation, and that's in the bottom left. And semantic segmentation, obviously, you're lumping all the sheep together, but you could also do instance segmentation, which is sort of the most burly version of the task that we're asking it to do, because now it's saying do pixel by pixel, but keep separate the different instances of a category like sheep. Okay, tricky to do. So those are the different terminologies we're going to use. Now let's dive into how they're done, right? So there are sort of old school techniques, classical approaches to image segmentation, and recently there are deep learning techniques. Okay, so let's start with the traditional ones, and then we'll move towards the most advanced ones. Okay. So first off is thresholding. And thresholding is probably something that you've come across before. If you've done photography, I remember some of the apps used to let you, right, if you took a picture of something and it was all kind of grayscale and you want to adjust the contrast so that the whites are really white and the darks are really dark, you can actually change the threshold. You can actually bring in the edges. So now what used to be grayscale before becomes black and white, and you can actually move where the middle is by adjusting the threshold value, right? Or if you want to force something to be a black and white image, you can do that. Like here I am in my tutorial on the bottom, on the right-hand side here. This is using image J with a clearly eutectic microstructure. And what I'm doing is I'm choosing a threshold value such that the dark phases and the light phases get separated in this microscopy image so that you could calculate, say, the area fraction, which might be related to the lever roll. And that's what we did in this video, which is kind of cool. So how does this thresholding work, right? All it is it really just says like your pixel belongs in one category or another. So this is good for two, segments, right? Two different regions, as it were. And the math for it is super simple. You just go through every single pixel in your image, and you're going to go pixel by pixel. Let's say if it's an XY grid, right? Along the X and the Y directions, you're going to examine the intensity, and then you're going to pass it through some sort of thresholding decision, right? And that decision is really easy. It says assign that pixel value 0 or a 1, so this will be a black or white image, right? If a certain criteria is met. If the intensity of that pixel at position, X and Y, right, of your grid is greater than a threshold value that you set, like here you can see on the right where I'm actually moving this bar left and right, you can change where that threshold sits at, then it gets assigned to 1, and otherwise it gets assigned to 0. So super simple. This is thresholding, and this is a type of image segmentation, right? Because we took a complicated image and we're able to break it into just 2 things. And from those, you can more easily calculate things like area fractions or continuity or whatever else, okay? That is image thresholding. Okay, let's then talk about edge detection, right? Edge detection is another sort of classical approach to image segmentation. This time, you're not just trying to figure out what are particles and what is background. Now we want to know where does the edge of my different particles lie, right? So for example, maybe on the left you have like a hand-drawn labeled image, and on the right you have the image segmentation model trying to reproduce that. How do we do that, right? So it's going to identify boundaries between different regions, and it's going to do that by looking for discontinuities in pixel intensity, right? If you look at like the profile of my face, right, compared to the background, my face should have a different intensity than, say, the background. That's the idea anyways, right? Like my hand in front of my shirt, it's got a different intensity relative to the thing behind it. So we're going to look for those differences in intensity, and we're going to use that to then do our edge detection. So the tools that we use to look for differences in intensity, there's various. They include Sobel points, or Sobel filters, Canny filters, Laplacian, Gaussian. There's a bunch of different ones. And so there's not one way to do edge detection. There's various depending on which filter you're using. But the idea is kind of the same. You're going to take and you're going to make a transformed version of your image, which is now going to highlight edges, we hope, by taking your original image and simply multiplying it by a filter, right? So we're going to go pixel by pixel or group of pixels by group of pixels, depending on the filter that you use. And we're going to multiply it by some sort of operator. So what you see here, the SX and SY would represent Sobel filters to find X and Y edges, right? It's going to try and find flat edges and vertical edges, but you could come up with other ones that find diagonals or color gradients. These don't have to just be black and white, right? And then once you have your gradient in your X and Y directions, you could convert that to your overall gradient by just taking, the square root of each of those squared. Okay, let's do an example of Sobel filtering. So let's imagine that the red numbers here on the grid represent your image. Now this is a really small thing. This is just a 6x4 image, right? But it can be as big as you want. But clearly you can see that the numbers, if they were to represent intensity, then we've got a darker half, that's where the 25s are, and a brighter half, that's where the 100s are. And then on the top left, you see GX and GY. So these are going to be the filters that we are going to use, and we're going to do dot products of these filters and then convolve it across the image. If you remember from our convolutional neural networks, we talked about taking a filter and convolving it across our image. That's what we're going to do here. So let's go ahead and do this as an example. Okay, I'm going to draw on my image here a 3x3 section, and that's going to be where we multiply our filter by. So by the time that we take a 3x3 filter and convolve it over a 6x4 region, that's going to leave us with a 4x2 image. So it is going to change the dimension of our image, right? It's going to have a 4x2 image at the end. Now, if we take this filter and we multiply it, we just do a dot product across that, we find that it's going to be, on the left-hand side, it's going to be -25 plus -50 plus -25. So it's a total of -100 coming from this part of the filter, right? The middle part is just going to be 0, so it's going to be -100, and then it's going to be plus +100. So the value that we're going to store in here is just 0, right? That filter doesn't produce any signal because all the pixels are the same. So now let's convolve it over one spot and see what happens. Okay, now I'm going to draw the blue bounding box, and we're going to do that same math over this box. So this time it's still -100 from the left, 0 from the middle, but now the right is going to be +100, +200, +100. So that's going to be +400 plus -100. So this value right here will be 300. It's hard to draw by hand, but you get the point, right? And when we convolve it again, it's going to be the exact same. This value will also be 300, right? And when we convolve it one more time, now it goes back to being 0. So in other words, our total image is going to be zeros in regions where there's no gradients, and then it's going to have these really high intensity values where there are gradients. And that is only identifying as we convolve this because of the shape of that filter. What would happen if we did that exact same process, but this time we're going to use the Sobel Y filter? Well, this time, if we do the math, let's just look at the first box, the purple box. That would be, going along the top, that would be positive 100, then 0, and then negative 100. So we would still have 0 in our first box. And then if we look at the dark blue filter area, now it would be positive 25 plus positive 50, so that's 75 plus positive 100. So that would be positive 175, then 0, and then it would be negative 175. So it's still 0. In fact, anywhere you do that filter, it's just going to be 0. Because the gradient in this data existed going from left to right along the x direction, our GX filter, our Sobel filter in the X one, is able to find it, but the Y is not. So that's an example of how these filters work. And they don't have to just be a 3x3. They can be more complicated ones, but that gives the idea of how these are going to actually transform an image to then make a version where these sort of edges have been highlighted. Okay, now the last traditional approach to image segmentation is something called region growing, okay? So region growing, I'll just read it here, it says starts with a set of seed points, and then it grows the regions that these seed points are in. So whatever your seed points are, you call that a region, right? And then it appends together the regions as they grow if the neighboring pixels have a similar property, say for example, the intensity of that pixel. Okay, so here's the math of the process. You start with a pixel I, right, PI, that is in some region R. So wherever that pixel lands, you define that as a region. In terms of colors, that might be white, green, or red, right? You could define how you wanted to these things, right? And then you look around that pixel, just consider its first immediate neighbors, for example. Those are PJ, the pixels in the same neighborhood. And then you either append them to that region or you don't append them to that region based off of some sort of similarity criterion, right? So for example, you're going to pass these through that criterion, CPJ. So for pixel J, for the pixel at point J, you're going to pass it through this criterion, which is basically saying true or false, where it might be like, is the intensity of pixel J, this neighbor pixel, minus some sort of thresholding, right? Minus the average intensity of the pixels in that region, is that less than some threshold? And if it's less than some threshold, then it gets added to that region. And then the region's intensity gets updated, right? The average intensity of that region gets updated after each step. So by starting with a bunch of seed points and then growing them outwards, eventually you're able to take this image on the left, which is grayscale, and convert it to just 3 different segments by doing region growing. And obviously it doesn't have to be 3, it could be any number of different segments of your choosing. But that would be image segmentation via region growing. Okay, so those are the 3 ways, and those have been used for material science. All 3 of these examples you've seen have all come from material science papers. So they've been used, but everything has changed with the arrival of UNet. So UNet was not actually invented by material scientists or chemists, right? This actually came out of the biomedical field, right? If you look at the authors, right, and the type of the paper, this is about biomedical image segmentation. And that makes sense because in medicine, we don't just want to classify, is there a disease, yes or no? That's part of it. But rather we want to know what part of the disease might be responsible, right? Why, when I look at this image, do I know that a certain disease is present? To do that, we need to be able to segment them, right? So we want to be able to localize and distinguish borders by doing classification on every pixel so that the input and the output share the same size. And that's the key thing that they did, is they made sure that the input, which is your regular image, and the output, the segmented model, is the same size. So here's how they did it. They call it UNet because of the shape of the neural network architecture. Kind of looks like a U, right? Now, in this process, there's a bunch of different things, right? If you look at the image from their paper, you can see that there are convolutions, right? That's the blue arrow going forward. Right here, that's these blue arrows going forward. There are copy and crop, more on that in just a second. And then there's the down red arrow is a max pooling operation. The up green is an up convolution, right? And then you have a convolution, right? So these are all things that we've seen before in convolutional neural networks, but it's the way that they get implemented, especially with the copy and crop, that creates this uniquely powerful UNet tool for image segmentation. So let's just go through the process. First, you have the process of encoding. This is what's called the contracting path or the encoder. And then once you've encoded it, we have an expanding path or a decoding path. So in the contracting path, our encoder, here's what happens. It's composed of repeated applications of two 3x3 convolutions, each of those being followed by a rectified linear unit, and then a 2x2 max pooling operation with a stride 2 for downsampling. Again, if you don't remember that, go back and watch our CNN video, our convolutional neural net video. At each downsampling step, therefore, the number of features is getting doubled, right? So you can see the shape of this thing. The original image was a 572 by a 572. You do your first convolutions and your image is changing, right? Because you're doing a 3x3 convolution. It's actually shrinking a little bit. It's going from a 572 to a 570 to a 568. But it's increasing depth, right? The additional channels comes from the filter, right? And then we do a pooling operation, which takes it from a 568 down to a 284, right? And then we're going to do convolutions again. And now it's down to a 280, and then pooling again down to a 140, right? So you're changing the dimension of your image until at the very end, your image is a 30 by 30 pixel, but it's 1024 deep, right? So we've radically changed the shape of our thing. And then you're just going to repeat that process backwards. Like, why go through the trouble? You go through the trouble because it allows you to add the copy and crop mechanism. So more on that in 1 second. First, the expanding path. This consists of essentially repeatedly upsampling your feature map by 2x2 convolutions. This is followed by a 2x2 convolution. This is an up convolution. And this halves the number of feature channels. And then concatenation with the cropped feature map from the contracting path. And then two 3x3 convolutions, each followed by a ReLU. Okay? So what is this copy and crop mechanism? So the copy and crop mechanism is clever because it allows you a concatenation of your feature maps that will ultimately tell us where the localized information is at. So this is from the paper. It says, the main contribution of UNet in this sense is that while upsampling in the network, we're also concatenating the higher resolution feature maps from the encoder network with the upsampled features in order to better learn representations with following convolutions. And since upsampling is a sparse operation, we need good prior from earlier stages to better represent the localization. Hence why in this expanding path over here, you've got the white boxes and the blue boxes. The white represents the copy and crop, where you're preserving the higher resolution version before it had been reduced, but you're adding the feature information from the upsampling, right? It's a clever approach, and it's turned out to be really powerful. And obviously there's a gazillion different versions of this because this is tunable, right? There's not just one UNet. Like, for example, here you see different ones. This time you have your convolutions that are 3x3. You've got a 2x2 pool, but they've changed the number of steps and the image sizes to start and begin. You could change the number of steps, right? All the way down, the number of layers. You don't have to be 3 or 4. You could do arbitrary number, right? This is a tunable architecture that ultimately you can explore to see what does the best job in terms of image segmentation for you. And while it's really good for segmentation, this exact same tool has been used also for super resolution. Because again, you're taking something in the process, you're taking something that's lower resolution, and you're learning how to restore that resolution. So you could take something maybe only had a grainy picture, and you could actually try and restore resolution. So I remember watching, CSI movies from the 90s, have a picture of a reflection on a bumper or a headlight of a car, and they'd zoom in, they'd say enhance, right? That enhance didn't exist. And now with something like UNet, we can do something like that. We can. It's all based off of probability, right? The information is not there in the image. But what you have is a neural network that's seen lots of examples with low-grade information, and it's learned to resolve that resolution by just seeing examples, which is pretty cool, right? But also generative models. And in our next video, when we talk about diffusion models, we will learn how UNet is actually useful for generative models. So jump ahead if you want to see that one. And then the other thing that we're seeing in the literature is that it's also possible to do transfer learning that lets us go beyond the so-called vanilla UNet architectures. So what do we mean? Where would we use transfer learning? Well, the idea is this, right? This contracting path, this first part here, they're not actually showing it in the typical U shape. They're showing it linear, but it's the same architecture. This contracting path is really just an encoder, right? You're encoding something into a new dimension, right? So why not leverage sort of beefy ImageNet encoders like VGG, which have their pre-trained weights, and then you could just focus on the decoder. So some UNets actually do that. For example, Turnhouse.net uses VGG11, one of the big, pre-trained ImageNet sort of models, as its encoder. Okay, and then the last thing we should talk about, if we're going to talk about image segmentation, has to be Meta's segment anything model. Meta, right, the company that creates Facebook and Instagram and WhatsApp and these others that bought some of those, right? It has released something called the segment anything model. This came out last year in 2023, and it is now currently the state of the art as far as I know. It is incredible. Here they describe it as follows. It is the world's first massive, scaled, promptable, interactive foundation image segmentation model. It's wild. Here you see an image where clearly it's a picture of a kitchen, a cutting board and walls and things. And yet you see that all these different regions have been segmented. The blue represents, interfaces between different things that have been segmented, but you've got two different cups that, while they look the same, are two different instances. You've got the orange, right? The slices are different from the parts, which are different from the wholes, right? It's able to do, and that's one of the key things, is that it's able to do whole, part, and then subparts, right? So you've got like the subparts of the knife showing up here. This is all what you can do with this segment anything model. So how does it work? Well, first off, it takes in two inputs. You have to provide it an image, obviously. If you want to segment something, you have to provide that image. But then it's really cool in that it allows you to also, in addition to the image, it doesn't just do it automatically. Instead, it then gives you the opportunity to provide a prompt. So you as a user get to decide how you want it to be segmented, and it's multimodal. There's different ways. You could just click on something and then it will prompt after that. You could draw a bounding box around something, or you can actually provide text, right? You can actually say find the scissor, for example, and it will be able to take that text or an image or a shaded region, whatever your prompt is, and it's going to do its best to try and figure out the part, the subpart, and the whole, right? Which is really cool. So the output of this is going to be three different masks representing the whole, the part, and the subpart. So that's pretty awesome. What's going on inside of this orange box that lets this happen? That's described in their paper, which I think you should check out, but we'll kind of briefly go through it. First off, so it has to have a loss. You have to teach it that it's getting things right and things wrong. One of the first things I noticed in this approach is that they don't just use a generic loss function. They do a combination of focal loss and dice loss in a 20-to-1 ratio. So what's the difference? Dice loss, that is just similar to your IOU. That stands for intersection over union, right? So you've got like IOUs calculated as your area of overlap versus your area of union for different things, right? And obviously you want to maximize that, right? But then your focal loss, it's interesting. It's actually a cross entropy loss. It says when you categorize something, right? When we do like classification models in machine learning, we typically use cross entropy loss because it's telling you which one you did versus the ones that were available. So this is doing a modified version of that. And what it does is that it allows you to place a higher weight, right? Because you have a weight as a tunable parameter. That's the gamma value that you see here. The gamma value in this equation is our tunable parameter, which is typically something between 0 and 5. But this essentially allows you to place a higher weight on categories that get misclassified, right? Things that should have been segmented separately that got misclassified, you place a higher weight on them. And then you place a lower weight on your easier examples, okay? So that's the first thing, is how it actually goes about doing this in terms of its loss function. And then secondly, is that something I think they did here that's really clever, is that they separated out the different prompts, right? Well, they separated out the two different encodings, right? Because you have your image that needs to be encoded, and you have your prompt from the user that needs to be encoded. And they were smart and realized that, hey, there's really big models out there. If you go back to our video and look at transformers, you saw how powerful transformers are for encoding. And so not surprisingly, things like Vision Transformer, VIT, are really good at encoding images that you can then take that encoding and you can do things with them. The problem is that some of these are huge, right? So this one, it says, an image is worth 16 times 16 words, transformers for image recognition at scale. And if you dive into that paper, you see that they have hundreds of millions of parameters in their model. And so this runs on a cloud-based GPU server. And so that's going to have slower latency, okay? If it's going to have slower latency, and it's not like crazy slow, but 0.15 seconds, is a little bit slow. So the idea is that's going to happen on the cloud because that would be way too slow to happen via the browser. Okay, so you're going to upload your image, and that will go through the cloud to get embedded. And then the user on through the website is actually via CPU going to be able to do their prompt either via text or points or drawing a box, right? They're going to be able to provide their prompt. These two embeddings get brought together, and then the decoder, the mask decoder, does its job and produces the final mask, right? So separating these two things was a clever approach that they did. By the way, SAM was trained on 11 million images, and they did that with 1 billion plus masks. And that is all open source. They open sourced this SA-1B, segment anything, 1 billion mask data set, so that you essentially have a massive trained data set. And this is why they're calling this a foundation model, right? Is they've released this in a way that is, they've done the hard work so that we don't have to by providing this really excellent curated list of labeled images based off of their masks, okay? So how does their encoder work, right? This vision encoder, image encoder, what's it actually doing? How's it work? Well, it's based off of the idea of a masked encoder, which are really powerful. I'm just going to read this from the paper. It says our MAEE, right? That's the masked encoder. Our masked encoder architecture. So it says during pre-training, a large random subset of image patches is masked out. So these don't have to be pixels. These could be chunks of your image. But the idea is that you're going to hide basically 75% of your image. So you see that this is not a full picture of a flamingo. It's bits of a flamingo, right? And then it says the encoder is applied to this small subset of visible patches. So the parts that are visible, those get passed through the encoder, right? And then it says mask tokens are introduced after the encoder. And then the full set of encoded patches and mask tokens is produced by a small decoder that reconstructs the image in pixels. After pre-training, the decoder is discarded, and then the encoder is applied to uncorrupted images. So this process of taking parts of your image and then comparing as you pass it through the encoder and decoder whether it got it right is a really powerful way to encode your image, right? So they do that during training, and then they toss out the decoder and they just keep the encoder, and that's how they achieve this image encoding process, which happens via GPU. Okay, so that's that part. What about the prompt encoder, right? So again, there's different ways you can do it. If you're encoding points where somebody just clicked on an image, then you're going to encode the position value in terms of X, Y position on the image, right? And then these embeddings are going to be used to indicate foreground versus background. You can do it with bounding boxes. This time you're going to encode the position of the upper left and the lower right hand points of the box that get drawn. Or if it's encoding text, right? If they're typing scissor, then you're going to have to do something like clip, where you're using a pre-trained clip embeddings. More on that when we get to neural networks for language coming later, right? But that will allow us to create an embedding with context-aware understanding of actual words and their meanings. Okay, so then comes the decoder architecture. So you've encoded the prompt, you've encoded the image. How do you get out of that this really cool mask that shows you the whole, the part, and the subpart? There's a lot going on here. So first off, right here in this box, over here in orange on the left-hand side, if you look at it, what you're basically seeing is there's 3 different layers there, okay? The bottommost layer, this is going to be self-attention with the prompt and the output tokens. And this is going to allow us to learn the contextual knowledge with respect to the prompt and the out embeddings, right? That's what attention does. It learns context between things. So then you go up one, and now you've got the prompt and the image, right? So now you're actually taking the image where you hadn't even seen the image before. You just took the output tokens and the prompt, right? Now you're going to take the image and it's going to take the prompt. This is going to be image attention, okay? So this will update the prompt and the out token, but now it has context of knowledge with respect to the image, right? And then the top layer of that box, the upper one, is going to be prompt attention, where again, now this time you're going to take the updates with your image embedding, and you're going to add to that contextual knowledge with respect to your prompt and your out tokens, right? And then they repeat that process 2 times. Attention is a great job of learning contextual interactions, but repeating it gives it more chances to learn that, right? And from that, we then output image-aware prompt embeddings. We have prompt-aware image embeddings, right? That's the output of these different things. You upsample this to get it to the right size. Meanwhile, your image-aware prompt embeddings you use to create your output token masks. These come in 3 different flavors, which we have via our loss function trained to identify whole, part, and subpart. then do a dot product of your upsampled image with these masks, and you end up with your final output masks. So very, very cool way, really representing state-of-the-art approach here. And then what I think is just the best of all is that Facebook, well, Meta, released this open source, which is so rad. I look at this, 5,000 forks, 42,000 stars, being watched by many people. Like, this is a really cool tool, and it's no surprise that people are using it like crazy. So that is all I have to say about image segmentation. We might do some follow-up videos on new advances with specific examples to material science, but that's the big picture of how image segmentation works. And the key thing to take away from that was UNet and what UNet is making possible, because that is going to make diffusion models make a lot more sense in our next video. So jump in. Let's see our next one.